Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear. Today I'm going to talk about something I think is really fascinating called the Mandelbrot set. You might have heard of it. It's a pretty famous set. It was discovered, I think, in 1984 by this, or no, 1978 by this guy on the left, Benoit Mandelbrot. He was a famous mathematician who studied chaos and fractals, and he discovered the Mandelbrot set, and he even coined the word fractal. And that's him on the left, and the picture next to him is a picture of the Mandelbrot set. Here's a bigger picture. And like I said, I think most of you are probably familiar with this. It's just an amazing set. It has infinite complexity. I mean, I'll show you some really beautiful pictures of it later on, but it's just a set with a very, very simple definition, but just a staggering complexity resulting from it. And here's actually the first picture that was ever made of the Mandelbrot set in 1978. At that time, we didn't have, really good computer graphics. This was actually done with text graphics. So obviously we can do much better now, like I showed you. But anyway, so what is this set? How do we define it? Well, it actually has a very simple definition. Here's the definition. In order to explain this definition, I first have to tell you a little bit about complex numbers. It's a complex sequence, meaning these numbers z0, zn plus 1, those are all what are known as complex numbers. Complex numbers are a two-dimensional extension of the real numbers, where you add a number called I, the imaginary unit. Complex numbers are just numbers of the form a plus bi, where a and b are arbitrary real numbers, and I is the square root of -1. So how do we define the Mandelbrot set? Well, it's simple. You take some arbitrary complex number c, uh, and then you form this sequence. So you start with z0, you set that equal to 0, and then for every value of n greater than or equal to 0, you set zn plus 1 equal to zn squared plus c. So for instance, z1 is going to be z0 squared plus c. Since z00, that's a c. C2 is going to be z1 squared plus c, that's c squared plus c. Keep going like that forever. And the way you define the Mandelbrot set, you say it's just the set of all complex numbers c such that the sequence converges. And it's pretty easy to determine whether or not an element of this sequence, well, it's easy to determine if it diverges. But first, let me just give you an example. So imagine c was 0.0 plus 0.2 plus 0.5 I. That's going to be the point, I think the top point in this kind of, see this blue diagram in the top right? Those are iterations. So the first iteration, I guess Z1 or C would be the point on top of this these blue points. And then when you keep iterating it, the points actually rotate 90 degrees counterclockwise each iteration. But not only do they rotate, they actually converge. And they end up converging on this point in the middle. So that is a point in the Mandelbrot set. The Mandelbrot set is the set of all these gray points in the complex plane. So since we picked a point C that was gray, the sequence converges. But if we picked a point outside, one of the white points, it would have diverged. And actually, it's not too hard to determine whether a point is outside the Mandelbrot set. You just wait until the absolute value gets to be greater than 2, and then it's easy to prove that once the absolute value is greater than 2, say Zn has absolute value greater than 2, then every other element of the sequence is also going to have absolute value greater than 2. As a matter of fact, the absolute values grow without limit. So once you get past 2, you don't have to do any more. And the way you get the colors in the pictures is you determine how many iterations it takes before the absolute value gets to be at least 2. So it's very easy to color in the points outside the Mandelbrot set. That's actually was more interesting than the set itself. And this is a zoomed in picture. I should show you the whole Mandelbrot set again. Notice that here's the whole Mandelbrot set. It's the black points in this diagram. And there's a main. It consists of a bunch of bulbs. The main bulb is shaped like a cardioid, a little bit of a sideways heart. All the other bulbs are circles. So there's a main bulb, and then there's a bunch of bulbs on top of that. And what this last picture I showed you was just to zoom in on one of those bulbs. This is actually a pretty small bulb, probably magnified by a factor of 10 or 20 or so. And then you can see there's smaller bulbs on top of that bulb. Like I said, this thing's a fractal. But not only that, I mean, I think these colors outside of this region are very beautiful. And it shows you just amazing structure. I mean, not only is this set fractal, meaning that it has detail on every scale, no matter how far you zoom in, it seems to have different details wherever you look. Just a really amazing set. So and here you got these little swirly patterns, and here you got a big. It looks kind of like a big flower with a bunch of leaves on it, and you just get structures like that wherever you look, and you even get magnified versions of the Mandelbrot set. This is a mini Mandelbrot set within the Mandelbrot set, and there's actually infinitely many of these. Pretty amazing. And here's one last picture I'm going to show. This is a part of a region called Seahorse Valley, and you have these little regions. You have these spirals, and you can zoom in on the spirals. I actually once watched a YouTube video where they zoomed in on a portion of Mandelbrot set by a factor of 10 to the 1,000th power. 1,000 powers of 10, if you can imagine that. And just to give you comparison, the universe, the observable universe, only has structures we know of for about 40 powers of 10. And actually, there's a very good short movie called Powers of 10. I don't know if you guys have seen this, but they actually do this. They zoom in from the whole observable universe to the size of a proton, which is like 40 powers of 10, and they do power of 10 in about 10 seconds. The video I watched, they were doing each power of 10, I think, in 1 second. And the video went on for like 15 minutes. So just amazing amount of complexity in the Mandelbrot set. Like I said, it's one of the most amazing things I've ever learned in math. So anyway, that's my video on the Mandelbrot set. I hope you enjoyed it, and I'll see you next time.